So hello, we're back again with another lecture for statics of rigid bodies. So we will be picking up from our previous topic that we have started about moments, but this time we will be studying how to compute moment about a specified axis. So before that, some learning objectives for this lecture. So from our syllabus is to apply the principles of moments in solving force and couple moment. That includes calculation of a moment about a specified axis and the calculation of the moment of a couple and a resultant moment. So later on we will be defining what is a couple and a moment of a couple, as well as finding the resultant of a couple moment system. So for the lecture outline, the first part would be the scalar and vector formulation of a moment about a specified axis, followed by example 1. Next would be moment of a couple and or couple moment, followed by example 2. And last is resultant couple moment and example 3. And at the end, you will be doing an activity, sheet work number 4. So let's start for about moment about a specified axis. So we learned earlier from our definition of a moment that it is composed of a force, a perpendicular distance, and the tendency to rotate. So in this case, as you can see here, the force is applied such on the first figure on the left, and the perpendicular distance here is d, and the tendency to rotate is, as you can see here, it's along the x and y plane, m sub o. So now just check the figure. This is basically a tire, and there are nuts that you are removing or installing using a tire wrench in such way. So you use a force going up to remove the nuts on the tire. In theory, this is your force, this is your perpendicular distance, and your tendency to rotate is such here, somewhere in the x and y plane. But in reality, the nut is not going or not turning in that direction, correct? The nut is turning in this direction, which is along the y-axis only, right? That's what happens when you do it actual, right? So then, if in theory the moment is somewhere here, as you can see here, but in reality the moment is projected along the y-axis. So for scalar analysis, if we want to find this moment along the y-axis, a specified axis, or let's say my, we also need to find the perpendicular distance from the force. So in this case, that is d sub y, and if you will study the triangle here, d sub y is approximately d cosine theta. So that is your moment arm. So to find the magnitude of m sub y, you need to multiply just the force with its perpendicular distance, and that is f times d sub y, or fd cosine theta. So I think you will be familiar with this one. What is two vectors and the cosine, the angle between them, that would be. Now let's go to the vector analysis of this. So as you can see, in theory, the moment is along the xy plane here, m sub o, which will have which can be found by doing the cross product of r, the moment arm, cross f, the force. But what we want to do is to find m sub y, which is our moment about the specified axis y, or let's say a specified axis a. But in this case, it's along the y, so it's m sub y. So here, the moment generated by r cross f is in the xy plane. What we want to find is the moment along y, which is a projection of the moment along the xy plane here, m sub o. M sub y is a projection of m sub o. And as we have learned earlier from our previous lessons, to find the projection of a vector into another plane, that's one of the applications of the dot product. That's why to find m sub y, you need to do the dot product of m sub o with the unit vector j, which is in the y axis. So that would be m sub y is equal to j dot m sub o, or we can further expand that as j dot r cross f. So as you can see, we will be doing dot product and cross product together. So still to derive the formula, so our derivation is based on this tire and this nut and the wrench. But in reality, what we really want to find is a projection along a specified axis. Let's name that axis as axis A. So if we have this position vector r, which is the moment arm, we have a force. We want to find the moment m sub o, that would just be equal to r cross f. And what we basically want to know is to find the projection along a specified axis. In this case, that's axis A, or we want to find m sub A. And what we need to do is to find the unit vector along the direction of A. In this case, that's called u sub A, and get the dot product of that with our moment m sub o. So in matrix form, so it's easier to do the cross product if you can write down the matrix, right? As you can remember, we have I, j, k, we have the x component, y component, and z component of the position vector or the moment arm, and on the bottom row would be the x, y, z components of the force. And we need to do the dot product of that. So I hope you can still remember how to do the dot product. The cross product is very fresh as it is only from last meeting. So if you can't remember that, kindly review our previous lessons. So the dot product is basically ua, xi, and so on, dot this, the matrix for the m sub o. So the general formula would be this one at the bottom. Kindly just read it, or if you don't want to memorize that, just do the matrix for the r and f components, or the cross product. Okay, now let's proceed to example 1. How will we do the combination of dot and cross product? So we have this arrangement in here. We have the dimensions there's a rod 0.6 meters in length, that's along the x-axis. There is a height of 0.3 meters along the z, and along the xy plane there is from A to B with such dimensions, and we have a force here 300 newtons. So what we need to do is to determine the moment which tends to rotate the rod, this rod, along the AB axis. So first of all, we want to visualize where is the rotation happening. So as you can see here, this is our force, and we have, let's say, something like a moment arm in here. Let's call it R. So what you want to do is R cross F, right? R cross F. So the moment occurs somewhere here, the original moment, right? So you have M sub O, but as you can see, there are restraints here. So if you apply the force at the other end at point C of this rod, the rotation will happen somewhere here, right, along the AB axis. So this has a length of what we call it RAB. Okay, so don't be confused, this would be R. So since this is a position vector RAB, we can also find the unit vector, let's call it UAB. And the tendency to rotate along AB, let's call it MAB. Okay, so this is what we're actually looking for, MAB. So determine the moment which tends to rotate the rod along the AB axis. So that moment is MAB. But what we have is 300 Newton force, the position vector, or let's call it RAC, and the M sub O, which occurs somewhere here. And what we want to know is the moment along MAB. Okay, so I hope you can analyze our structure in such a way so that the calculation will come easy on you. So let's write here our givens. So this is already our given. If you can draw this structure along with the additional variables that you're going to use for the calculations. So this is our given. So what's our given? We have the magnitude of a force which is equal to 300 newtons. What else? So what do we actually need? We need to find the MO first, right? We need to find this first, and we will do that by taking the cross product of the position vector RAC and the 300 Newton force. But as we have learned from before, it is easier if the position vector is only going on one particular axis, right? The more zeros there is in the matrix, the better. So in this case, you should determine the easiest route and determine what is the position vector, which will give us an easier time. So at this point, let's also write down here another point. Let's call it point D. So the force is still intersecting point D, right? And from point A to point D, that is actually another position vector that you can use in your R cross F, right? You need to do R cross F. So if we can find this position vector here from A to D, let's call it, we have RAD. So we can still use RAC, but that will give us like 2 dimensions along the Z and along the X, and the component in the Y is 0. So that's also easy, but using RAD is easier since it's only along the X axis, right? And according to the principle of moments, we can, or the principle of transmissibility, we can actually use that position vector. Okay, again, no problem using RAC, you will arrive in the same answer. We already proven that from the previous examples, but RAD will give us an easier time in the calculation. So what we need to do is to determine RAD. In this case, F. So for vector F, let's write vector F first. For vector F, what is vector F? This is actually 300 newtons going down along the Z axis, so that's negative 300 Z newtons. I hope you can follow that. That's negative 300 Z. Since it's going down along the direction of the negative Z, this is the Cartesian form, the CVF of the force. We need that because we're going to do the matrix later. And what we need is RAD. I hope it's already clear why we chose that position vector, because it will give us the more zeros in the matrix. That's 0.6 meters, or the Cartesian form of that would be that's only along the x-axis, so that's positive 0.6 meters, 0.6 I. So we're still using the right-handed coordinate systems. If you've forgotten already the sign convention for that, please review it. That would be okay. So basically what we need to do is to find the cross of this R cross F using these two. That will look very easy on our matrix, since this is only one dimension and this is also one dimension. But what we need is also to find, okay, so that would be on our requireds. Okay, so everything is given here. So what is required? So we need to solve for, what do we need? We can already have the matrix R cross F. What we need is UAB. So in that case, we also need RAB. And how do we find RAB? That is to find the Cartesian form of the position vector RAB from A to B. And I hope you can still remember how to do that. That would just be the head minus tail, right? So the origin is 0. So that's 0, 0. It means that RAB would just be, okay, so first of all, our required is the moment along AB. So finding the RAB is just accessory to finding MAB. So we will do that in our solution, but what we're really required to find is to find the vector MAB. Okay, so let's go to our solution. So let me write that down here. So we can already find our AD cross F. What remains is to find the dot product of that with U A B, and that would be equal to our M A B, which we are trying to find here. So to find U A B, we need to find our A B, and according to our measurements there, this is 0.4 along the X, 0.4 meters along X, and 0.2 meters along Y, and 0 along the Z axis. So we can find our AB, or we can write the Cartesian form of our AB as 0.4I plus, so they are both in the positive axis, so 0.2J. That would be in meters, and what we need is to divide that with its magnitude. So the magnitude of that would be the square root of the sum of the squares of the components, which is 0.4 squared plus 0.2 squared. So that's 0.4 squared plus 0.2 squared of, that's 0.4472, and we divide 0.4 with that, so 0.4 divided by, that gives us approximately 0.8944 I, and half of that, since we need to divide 0.2 as well, which is 0.4472 J. So this is, since that's both in meters, that's unitless, and this is equal to our, this is our U A B. We're actually looking for this one. Since we already have the Cartesian form of our U A B, we can now proceed to do the cross product that we are looking for. That would be M. We are looking for MAB. That would be UAB dot RAD cross F. So what we're gonna do here is to write it in matrix form. So this would just be equal to, so recall that our AD cross F, or the moment, is will yield a vector, right? So that's M sub O. This is just the same as saying, let me just write it here, saying UAB a vector dot another vector, which is M sub O, or AD cross F. We are trying to find the projection along the AB axis, and the dot product is defined as a scalar. Okay, so the answer here is a scalar. Okay, so let's write down the matrix. So for that, the matrix will look something like this. Okay, so you have, at the top column you will have a 0.8944 and 0.4472 for the Y component, and 0 for the Z component. The next would be for the RAD, which is along the X opponent 0.6 meters, right? 0.6 meters, and 0 along y and 0 along z. For the force, that would be 0 in x, 0 in y, and negative 300 in z, right? Okay, so you have to write your matrix like this, and we will follow the method for the cross product for that. I hope you can still remember that, and let's do it here. Maybe use a red one. Okay. For the first, the I, or the, yes, correct, for the x axis, which is 0.8944. Let's write it here. So our first expression here would be 0.8944 multiplied by, I hope you can still remember what we need to do here is to block this, right? Like cover it up and do cross of this and cross of that. Okay, so I will just erase that, and just for recall, that is just for recall. Okay, so that would be 0 times negative 300, so that's 0 minus 0 times 0. So the first expression is very much 0. The next is the second expression for the cross product will have a negative sign, right? Negative sign. Okay, so that would be 0.4472. If you block this one, we will actually have a value here. That would be times 0.6 times negative 300. And that's actually newtons, and that's not force. Sorry. 0.6 meters minus 0 times 0. So that's just 0. So for the second expression, we actually have a value here. Okay. For the third expression, that is 0 multiplied by whatever you find here. So that's basically 0. So if the first expression is 0, the next one is, the last one is 0. We only need to solve the middle one, which will yield a positive value, since that's negative 300 times 0.6 times negative 0.4472. That's actually 80.5. Okay, so our value is 80.5 Newton meter. So that is for the magnitude of our this is the magnitude of our moment along MAB. So what we need is the Cartesian vector form of that, and we can do that by multiplying it with the unit vector along AB, which is UAB. So let me do that on the top here. So MAB, would just be equal to UAB times the magnitude of MAB. So that's 0.8944 times 80.5. which will give us approximately 72. That's 72i plus, that's 0.4472 times 80.5, that would be 36 plus 36j. This is the Cartesian vector form of Newton meter of our, so that's actually what we're looking for. So additionally, it can be asked in your future assessments or exams or problem solving tests to find the angles, and I know you already have that taken care of. You just need to find the direction cosines. Okay, so this is for our let's compile our answers here. So we have here the answer. So the Cartesian form would be for M A B is 72i plus 36j. That would be in Newton meter, and the magnitude is 80.5. Okay, so please don't forget to always write your complete solutions with the 4 sections along with the answer. So now we already solved the problem to determine the moment along the AB axis, which is MAB. So that is how you do the combination of the dot and cross products. Now let's proceed to the next topic, which is moment of a couple. First, we define what is a couple. So a couple is just two parallel forces. As you can see here, you have force F and you have force negative F, since they have the same magnitude but opposite direction. So if the other one is F, the other one is negative F, and they are parallel forces separated by a perpendicular distance between them. As you can see here, we have R. Okay, so a couple composed of two parallel forces, have the same magnitude, have opposite direction, and separated by a perpendicular distance between them. So if we do a force summation of a couple, you will have the resultant force of 0, right? So this is positive F plus negative F, that would just be equal to 0. So since the resultant force is 0, but there is a tendency to rotate, so only produce a rotation or a tendency to rotate, and that tendency to rotate is called the moment of a couple or the couple moment. So the moment produced by a couple, and it is a free vector. So if you can recall our discussions about types of vectors, so the couple moment is a free vector. Okay, so for the scalar formulation of our moment, that would just be equal to force times the distance. In this case, that would be M equals Fd. So the moment is still can be calculated from R cross F. Okay, if you can see here, RB cross F, that's one moment, plus another moment, which is RA cross negative F, that would just be equal to RB minus RA cross F. So if you will follow the triangle vector addition of disposition vectors here, this would just be equal to R. So RB minus RA will be equal to R. Did you follow that? That's head to tail addition. So the moment is just equal to the perpendicular distance between the the forces, and the magnitude or the force vector here. That would be our couple. So for illustration, we have here a valve. So if we want to turn the valve, we exert 30 Newton force from one hand, and another 30 Newton force from the other hand. As you can see, this is a couple, since there are two forces equal in magnitude but opposite in direction, and there is a perpendicular distance between them. So an equivalent couple are two couples that produce a moment with the same magnitude and direction. So quick math here. So this is 30 newtons. To find the moment, that would be 30 times 0.4, the moment arm. That would give you 12 newton meter. So for the second illustration, you exert this is the same valve, but you just shorten the moment arm to 0.3, but you exert more force. That's 40 newtons and 40 newtons opposite. So 40 times 0.3, that is the same, that's 12 newton meter. So we can call this to as equivalent couple, since they will produce a moment with the same magnitude and direction. So in reality, if you are trying to turn a valve here, it is better to have a longer moment arm, since you're going to exert less force. See here, if your arm is 0.4, you just need to exert 30 newtons. If your moment arm is 0.3, you need to exert more force, which is 40 newtons. So that is your equivalent couple. Okay, so while we already defined the definition of a couple, we also have the resultant couple moment. So you have a couple moment M1 resulting from one couple, and couple moment M2 resulting from another couple, and we just want to find the resultant of that, then that is M sub r. So the same thing, that would just be the summation of this couple moments M1 and M2. So summation of the R cross F. Now let's proceed to example 2. So our task is to determine the couple moment acting on the pipe. So as you can see, we have 25 pound force going down and another 25 pound force going up along the Z axis. So this is basically a couple. There is a perpendicular distance between them. In this case, that is 8 inches, and we have this arrangement here, the rod. So if you exert a force here and there, that is a couple. If you have a couple, you also have a couple moment, and that is what we're going to find here. So determine the couple moment acting on the pipe. So for this problem, we need to define the Cartesian forms of the vectors that we are going to use. That includes the force and the position vector. So let's determine what is our given. So given is a couple of 25 pounds, that's F. What we want to use is the positive one. So F, that would be 25 pounds or 25 K. We'll use the positive one, okay? So this one is 25 K. This one is negative 25 K pounds. So that's the Cartesian form of the force. We need that because we're going to do the cross product, and we also need the RAB, the Cartesian form as well. So where's RAB? RAB is actually from here to here. This is RAB. And the magnitude of RAB is actually 6 inches. But what is the Cartesian vector form of that? So as you can see, we have in the x direction, there's a triangle here. X direction and the z direction. So this has two components. The x direction would be okay, so this is the x direction, so that's positive, and the z direction for the component of RAB is going down, so that's negative. So it's basically the x component is 6 cosine 30 degrees, that's I, minus, since the other component is going down, that's opposite 30 degrees, so that's 6 sine 30 degrees. And that k, you have a k here, so there is no j since there is no component of RAB in the y-axis. This is in inches. What we need is the cross of this to determine the couple moment. So let's go right at it. Let me write it here, the solution. So solution for this one, we already defined our, oh by the way, we need to determine first the what is required. So this is required is actually the couple moment m, which is just equal to RAB cross F. So this is our required. So in our solution, we need to carry out this. Let me write it down again here. M is equal to RAB cross F. In matrix form, that would be, let's write it down here, the vectors I will write in blue. That would be I, J, and K. And for the position vector RAB, let's write it in green. RAB is, that's 6 cosine 30 in the I, 0 in J, and 6 sine 30. Sorry, that would be negative 6 sine 30 in K. For the force vector, we have, it's only along the K or the Z axis, that's 25 pounds. Okay, so we will just carry out the cross product of this. So if you already memorized the sequence for the cross product, no need to write this matrix, but for me it's easier to write this matrix than to memorize the whole formula. So let's just write down this matrix. So this would give us, for I, that would just be, for the I component, that would be 0 times 25, so that's 0, minus negative 6 sine 30, that's actually negative 3. So negative, there's nothing here, there's actually negative 3 times 0, I, that is I. So looks like I would have no value, that's also 0. The next symbol between our cross product is a minus, so that's for J. You have, okay, actually you have a value here because we have 6 cosine 30 times 25 pounds. So it's easier if there are more zeros, right? Minus negative 6, that's negative 3 times 0 again. So this whole thing here would be j. So we actually have a value here since we have 6 cosine 30 times 25, and that is, we have a negative sign here. Okay, so the next one is plus, for the k, I think we will also have a 0 value since that's 6 cosine 30. So let's just write it anyway for just to visualize it. 0 minus 0 times 0, that is k. Okay, so it looks like we only have the value along the j vector, which is getting our calculators. That would be cosine 30 times 6 times 25, that's approximately 75 square root of 3, and that is negative. Okay, so let me write it somewhere here. So according to our cross product, this would be equal to 75 square root of 3, let's be exact. Okay, j, and that is negative. Okay, this is pound inch. So this is the Cartesian form of our. So now that we have calculated it, it's better to visualize it. It's actually, let's go back to our, let's go back here. So it's actually, since it's on the j, it's going on the j, it's somewhere here going negative j. That's why your moment is somewhere here. Just to visualize it, it says it's negative 75 square root of 3 j. So this is the j, or the y-axis. So it means our couple occurs somewhere here. And don't forget, it's actually a free vector, so you really don't need to state this. But in reality, you can see if the forces are going here, the moment is somewhere in the middle of the, like in the valve illustration. Okay, so that's example 2. So I hope you can follow and you already develop your sequence for doing the cross product. Okay, now let's proceed to, okay, this is just some illustration of, you can actually use deriving RA and RB and doing the cross product of RA cross negative 25 and RB cross positive 25, but you will just subtract the two, so it's easier to use just one position vector, which is RAB. You will have the same result if you use two cross products, but who wants to do two cross products, right? You just want to do one, so it's easier to find RAB and the cross with 25 with the force. Now let's have an example 3. This is resultant couple moment. So express the two couples. You have two couples here, 150 newtons with a 0.4 perpendicular distance between them, and 125 newtons with 0.3 perpendicular distance between them. So this is the illustration. So express the two couples acting on the pipe as a resultant couple. So what we need to do is to do the cross let's say R1 cross F1, and the summation of that plus R2 cross F2. So to further illustrate, this is actually what we're looking for. We have a couple moment M sub 1 and another couple moment M sub 2 resulting from the two couples, and what we want to know is the resultant couple moment. So let's do. So now that we can visualize it this way, you can see that M1 is acting along the x-axis alone. So that makes it easier to get the Cartesian vector form of M1. The trick here is to find the Cartesian vector form of M2. So let's go back and write down our givens. So our given here, we have a given. So we have force 1. Let's name force 1 as 150 newtons. And the D1, that's DI, as 0.4 meters. So we can easily find the magnitude of M1 here in the Cartesian vector form, since it's acting only along the X. And we have force 2, which is 125 newtons, and D2, which is 0.3 meters. So what is required is let me write down here the required. What's required from you is resultant component moment, or M sub r, in Cartesian form as well. Okay, so that M sub r is just equal to the summation of the couple moments, which is M sub 1 plus M sub 2. Okay, so let's start with the easier one, which is M sub 1. So for our solution right here, again, M sub 1 would just be in the scalar formulation of that would be 150 newtons multiplied by the moment arm, which is 0.4 meters. That's approximately 150 by 0.4, 60 newton meters. So this is 60 newton meters. And from what we see here, it's acting along the x-axis, so it's easy to say that the Cartesian form of that would be, let me write down the Cartesian form of M1 is just, it's going along the positive, so it's positive 60 I Newton meter. So that's the Cartesian form of M1. So we need to write the Cartesian form since we are going to do summations later. So for M2, what do we have in M2? Let's take a look. So this is M2 is somewhere here, right? If you're going to use the right hand rule, the moment would be somewhere here. That's M2. So what we need here is we actually don't know which is positive and which is negative from these two forces, right? So actually you can use either of them, but I will prefer to use the positive direction of the position vector or the moment arm, which is 0.3 meters. So this 0.3 meters is also acting along the x-axis. So if we take the positive vector for that, we have to use this force here, the one going down, this 125 newton here. I hope you can see it. I will just encircle it, this one, and it is a 3-4-5 triangle, so we can use this ratio to find the components. Again, you can also use the other one. It also has a 3-4-5 ratio, but then if you want to use that, you need to use the negative 0.3, since it's going the opposite of the positive x-axis. Okay, is that understood? So I'm just using this one here since I'm going to use the moment arm, which is in the positive direction. If you want to use the moment arm which is in the negative direction, you use the other, this one, use the other force. Okay, so that will give you the same result, but for me I will use the first one. So that's 3 on Z, 4 on Y, okay, and 5. So let's write the let's write the Cartesian form of this force here. So force 2, I will write it here for better illustration. So force 2, what is the Cartesian form of that? That would just be, since we have the magnitude, that's 125. We don't have anything on the Z, right? So that's 125 times 4 over 5. So this is 4/5. So that's 25 over 4. That's actually 100. J, right? That's in the y-axis, positive. And the next one would be, it's going down. So that's negative 125 times 3 over 5. K. Did you see that? You see it's, the components are going in the positive y and the negative j. That's why you have this. So newtons. Okay, so I just write it here so that we can visualize. Okay, so this is 125 divided by 5. That's 25 times 4. This is 100 j minus 125 divided by 5. That's 25 times 2. That's 75. Okay, so remember that, and let's write it here. So from that analogy and calculation, we can see that the Cartesian vector form of m sub 2, let's write it in green. So m sub 2 is equal to 100g. Oh, this is interesting. This is easy since you have I component and 0 in j and k. Here the I component is 0. You have k. You just need to paste whatever we find. And minus 75k. Oh, sorry. This is actually not m sub 2. This is f sub 2. Sorry, that is my mistake. We still need to do the cross, unfortunately. So this is f sub 2 only. Okay, this is newtons. So actually m sub 2 is equal to the cross of the it's r cross f, or r sub 2 cross f sub 2, or r sub 2, as we have mentioned earlier, will have positive 0.3 I, right? Since we chose, let me just go back there to explain. Since we chose this force, we need to use the positive going this direction, positive 0.3. So that's 0.3 I. So that's 0.3 I meters cross this one. Let me write that down quickly. J minus 75k. So that is m2. We need to do the, let me do the matrix in black. So you have ijk, ijk. So don't get tired to write this matrix. It will be very easy. It will be easier for you if you can write this matrix. So the next is 0, that's 100, and negative 75. So for this one, it's actually, let me write it somewhere here. So for the I component, that would be 0 times negative 75, that's 0, minus 0 times 100, so that's 0. No, so let's not write that down. Let's go to G. That would be negative. Okay, the first one, let's write it as only 0. So 0 minus, this would be 0.3 meters times negative 75 newtons, minus 0 times 0 minus 0, that would be your G. And lastly, K would be, that is a plus, that's 0.3 meters times 100 newtons, minus 0, that's K. That is in Newton meter. Okay, so this is 0.3 times negative 75. That's negative, but times negative, so that's positive. Okay, so that's 22.5 G plus 300. Oh, sorry, plus 30 K. That would be Newton meter. Okay, so this is actually your M2. So if we will do the summation of R cross F, that would just equal the resultant moment. This is M, sorry. This is I, J, and K. So we can write down our, let me write down here the section for the answers. Our resultant moment is MR. We just need to add M1 and M2. So since M1 is just I and M2 is J and K, we just write that down straight ahead. So that's 60I plus 22.5 J plus 30 K Newton meter. That is the Cartesian form, and we can also find the magnitude of that. So the magnitude would be the sum of the squares, 60 squared plus 22.5 squared plus 30 squared, square root of that. So that's, let me type that, 60 squared plus 2.5 squared plus 30 squared, square root of the answer, that would be approximately 70.75 Newton meter. So let's go back. That's positive I, positive J, and positive K. So if we go back to our illustration here, okay, this is going to the positive X, positive Y, and positive Z. Okay, so that is our MR. This is, so let me write it here. So MR is approximately 70.75 Newton meter, and the Cartesian form is 60I 60I plus 22.5J plus 30K. Okay, so you should be able to come up with this answer. Okay. So now let's answer another example. This is now in 2 dimensions. So what we need to do is to determine the resultant couple moment of the three couples. So we have 6 forces here, and we have 3 couples. We have F1, this is negative F1, this F2, this is F2, negative F2, and F3, negative F3. So we have 3 couples. So what we need is to determine the resultant couple moment. This is in 3 dimensions. So what we're going to do is to first, of course, identify our givens. So our given here, we have F1 200 pounds, we have D1, that's 4 feet, we have F2 for 50 pounds, and D2 3 feet, we have F3 300 pounds, and D3 5 feet. So what we want to find is the resultant couple moment, or MR. So since this is just 2 dimensions, we're just looking for the magnitude. So what's the solution here? So solution, we just need to identify a convention for our moment. So let's say summation of the moments where counterclockwise is positive. So it's up to you to determine which is the positive direction. In this case, I want to do counterclockwise as positive. So let's do the summation and identify which moments will give us the positive the which couple moments will give us clockwise rotation. Let's look for force 1 or couple moment 1. If we will rotate it in this way, what is the rotation? It's actually going there, right? So it's clockwise, so it means it's negative. So that's negative F1 D1. Did you follow that? Since we say that in our summation of moments, the clockwise direction is positive, and since F1 D1 will rotate it clockwise, opposite counterclockwise, that would give us a negative moment, negative F1 D1. What about F2? F2 will rotate counterclockwise, so that's positive F2 D2. What about F3? F3 will rotate clockwise as well, so that's negative F3 D3. So carrying out all this to solve for the resultant moment, that's negative 200 pounds times 4 feet plus positive 450. Just do it in your calculators and it will be quick. That's 3 feet. But of course, be very careful with your sign convention and identify which moments will turn clockwise and which ones will turn counterclockwise. And we just need to do the math here. So that's approximately, this will give us a negative answer. That's negative 950 pound-feet. So what does that say? If we have negative 950 pound-feet, first of all, we assumed that the summation of the moments will turn anti-clockwise as positive. Since we find a negative answer, it means that that is opposite of our assumption. So it's safe to say that the moment summation of MR is, just write it as 950 pound-feet and the direction is clockwise. Okay, so it doesn't matter here if your assumption is clockwise, you will arrive at a positive 950 pound-feet answer and you will still write it as 950 pound-feet in the clockwise direction. Okay, so that is our solution for this problem. So that would be all for this lecture. As always, thank you for your attention. So this is our source, still our reference book, Engineering Mechanics Statics, 14th edition by Russell Hibbeler, and this can be found in pages 145 to 159. If you have clarifications, just use our Q&A link or send me an email. And if you want more examples, you can check out our book. There are more examples there. So thank you and good luck.